Hello and welcome to your ultimate guide for the D320 OA, Managing Cloud Security course. My goal today is simple: give you everything you need to fully understand the key concepts, master them, and walk into your D320 OA exam with total confidence. In this video we'll cover cloud characteristics, service models, deployment models, cloud roles and cloud security. And remember, our website offers free exam guides and practice questions to help you ace your D320 OA exam. You'll find the link in the description below, so be sure to check it out and get the resources you need to study smarter, not harder. So let's dive right in. Let's start with what cloud computing really means in today's technology landscape. When we talk about cloud computing, we're describing a revolutionary model that has completely transformed how organizations consume and manage IT resources. Think about how businesses used to operate. They'd purchase massive amounts of hardware, maintain enormous data centers, and constantly worry about whether they had enough capacity for peak times or if they were wasting money on idle resources during quiet periods. Cloud computing changes all of that by providing a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources. These resources include networks, servers, storage, applications, and services that can be rapidly provisioned and released with minimal management effort or service provider interaction. Now let me break down the 5 essential characteristics that define cloud computing, and these are absolutely critical for your exam. First, we have broad network access, which means cloud services are consistently accessible through standard mechanisms. Imagine you're working from a coffee shop in Bangkok, using your laptop to access your company's cloud-based customer relationship management system. Later that day, you switch to your tablet at home, and the next morning you're using your smartphone during your commute. The beauty of broad network access is that regardless of your device, operating system, or location, you can seamlessly access the same services through standard web browsers or applications. This is achieved through sophisticated technologies like advanced routing techniques, load balancers, and multi-site hosting that work behind the scenes to ensure consistent availability. The second characteristic is on-demand self-service, and this is where cloud computing really shows its power. Picture this scenario: your online retail company suddenly experiences a viral social media moment, and traffic to your website increases by 500% overnight. In a traditional IT environment, you'd be scrambling to order new servers, wait for delivery, configure them, and hope you can handle the load before customers get frustrated and leave. But with on-demand self-service, you can scale your compute and storage resources in real time, with just a few clicks or even automatically, without any human intervention from your cloud provider. The resources are provisioned instantly, allowing you to meet demand exactly when you need it. Resource pooling is the third characteristic, and it's the secret sauce that makes cloud computing economically viable for both providers and customers. Cloud providers operate on a multi-tenant model, where multiple customers share the same underlying physical infrastructure. Now, I know what you might be thinking. Doesn't sharing resources with other companies create security risks? Well, that's where virtualization and sophisticated isolation techniques come into play, which we'll explore in detail later. The key point here is that through resource pooling, providers can make massive capital investments in state-of-the-art data centers, cutting-edge hardware, and redundant systems that no single organization could afford on its own. These resources are then dynamically allocated based on demand, ensuring optimal utilization and cost-effectiveness for everyone involved. Rapid elasticity, our fourth characteristic, takes the concept of scalability to an entirely new level. Let me paint you a picture with a real-world example. Consider a tax preparation company that experiences 80% of its annual traffic during the 3 months of tax season. In a traditional model, they'd need to maintain infrastructure capable of handling peak tax season load all year round, essentially wasting resources for 9 months. With rapid elasticity, they can scale up their infrastructure by 10 times or more during tax season, then scale it right back down when demand decreases. This scaling happens in minutes or even seconds. not the weeks or months it would take in a traditional environment. The infrastructure grows and shrinks like an elastic band, always matching your actual needs. The fifth and final essential characteristic is measured or metered service, which fundamentally changes how organizations budget for IT resources. Instead of massive capital expenditures for equipment that might be underutilized, you pay only for what you actually use. It's similar to your electricity bill. You don't buy the power plant, you just pay for the kilowatts you consume. This model provides complete transparency into resource consumption, detailed billing information, and the ability to forecast costs based on actual usage patterns. For your exam, remember that this metered approach enables organizations to transform IT costs from capital expenditures to operational expenditures, which has significant accounting and budgeting advantages. Now, speaking of exam preparation, I want to mention that I've developed over 300 completely free practice questions specifically designed for the Managing Cloud Security D320 exam. These questions cover everything we're discussing today and will help reinforce your understanding of these critical concepts. You'll find the link in the description, and I strongly encourage you to work through them as they're structured to mirror the actual exam format and difficulty level. Let's dive into the cloud computing service models, which form the backbone of how cloud services are delivered and consumed. Understanding these models is absolutely crucial for your exam success, as they determine the division of responsibilities between cloud providers and customers. We have three primary service models: Infrastructure as a Service or IaaS, Platform as a Service or PaaS, and Software as a Service or SaaS. Each model represents a different level of abstraction and management responsibility, and I'm going to explain each one in detail with practical examples that will stick in your memory. Infrastructure as a Service, IaaS, is the most fundamental cloud service model. In IaaS, the cloud provider supplies the basic computing infrastructure, physical servers, storage systems, networking equipment, and the virtualization layer. As the customer, you're responsible for everything from the operating system up. Think of IaaS like renting an unfurnished apartment. The building owner provides the physical space, walls, plumbing, and electricity, but you bring your own furniture, appliances, and decorations. Similarly, with IaaS, you install and manage your own operating systems, middleware, runtime environments, applications, and data. Popular examples include Amazon Web Services EC2, Microsoft Azure Virtual Machines, and Google Compute Engine. Organizations often choose IaaS when they need maximum control over their environment and want to lift and shift existing applications to the cloud without modification, or require specific operating system configurations that aren't available in higher-level service models. Let me share a practical scenario to cement this concept. Imagine a financial services company that has developed proprietary trading algorithms running on a highly customized Linux distribution with specific kernel modifications for low-latency processing. They choose IaaS because they need complete control over the operating system configuration, can install their specialized software stack, and can tune every aspect of the system for optimal performance. The cloud provider handles the physical infrastructure, power, cooling, and network connectivity, while the company maintains full control over everything else. Platform as a Service, PaaS, builds upon IaaS by adding another layer of abstraction. In PaaS, the cloud provider manages not just the infrastructure, but also the operating systems, middleware, and runtime environments. You as the customer focus solely on developing and deploying your applications and managing your data. Returning to our apartment analogy, PaaS is like renting a furnished apartment with appliances included. You just bring your personal belongings and start living. Popular PaaS examples include Google App Engine, Microsoft Azure App Service, and Heroku. This model is particularly attractive for development teams because it eliminates the overhead of managing operating systems, applying security patches, and maintaining middleware components. Here's a concrete example that illustrates PaaS perfectly. A startup is developing a new mobile application that needs a back-end API, database, and authentication service. Instead of spending weeks setting up servers, installing database software, configuring load balancers, and implementing authentication systems, they use a PaaS solution. The platform provides pre-configured database services, automatic scaling capabilities, integrated authentication modules, and built-in monitoring tools. The developers simply write their application code, define their database schema, and deploy. The platform handles everything else, including automatic scaling during traffic spikes, operating system updates, and security patches. This allows the startup to focus on what differentiates their business, their unique application logic, rather than infrastructure management. Software as a service, SaaS, represents the highest level of abstraction in cloud service models. In SaaS, the cloud provider manages everything: infrastructure, operating systems, middleware, applications, and even application configuration. As the customer, you simply use the application through a web browser or thin client. This is like staying in a full-service hotel where everything is provided and maintained for you. You just show up and use the facilities. Common SaaS examples include Microsoft Office 365, Salesforce, Google Workspace, and QuickBooks Online. These applications are accessed through web browsers, require no installation, and are automatically updated by the provider. Let me illustrate SaaS with a real-world scenario. A marketing agency needs customer relationship management capabilities. Instead of purchasing CRM software licenses, installing the software on servers, maintaining databases, applying updates, and backing up data, they subscribe to Salesforce. Their employees simply log in through web browsers, enter customer information, track sales opportunities, and generate reports. The agency doesn't worry about server capacity, software updates, database optimization, or backup procedures. Salesforce handles all of that. The agency pays a monthly, per-user fee and focuses entirely on using the application to manage customer relationships, not on managing the technology itself. What we just covered about these service models appears frequently on the exam, particularly questions about responsibility boundaries and appropriate use cases. That's exactly why those free practice questions I mentioned earlier include numerous scenarios where you need to identify the correct service model for specific business requirements. These questions will help you develop the pattern recognition skills necessary to quickly identify the appropriate model during your actual exam. Moving on to cloud deployment models, which describe the ownership and accessibility of cloud resources. These models are just as important as service models for your exam, as they determine who can access the cloud environment and how resources are shared. We have 4 primary deployment models: public, private, community, and hybrid clouds. Each model has distinct characteristics, benefits, and challenges that you need to understand thoroughly. Public clouds are what most people think of when they hear cloud computing. In a public cloud, the infrastructure is owned and operated by a third-party cloud service provider and delivered over the public internet. Resources are shared among multiple organizations in a multi-tenant environment. Think of a public cloud like a commercial airline. You don't own the plane, you share it with other passengers, but you get from point A to point B efficiently and cost-effectively. Major public cloud providers include Amazon Web Services, Microsoft Azure, Google Cloud Platform, and Alibaba Cloud. The key advantages of public clouds include no capital expenditure for hardware, no maintenance responsibilities, virtually unlimited scalability, and pay-as-you-go pricing models. However, you must also consider that you're sharing infrastructure with other organizations, which may raise concerns about data isolation, compliance requirements, and performance predictability. Private clouds are dedicated environments used exclusively by a single organization. The infrastructure might be owned, managed, and operated by the organization itself, by a third party, or by some combination of both, and it might be hosted on-premises or off-premises. The defining characteristic is that resources are not shared with other organizations. Think of a private cloud like owning your own corporate jet. It's exclusively yours, configured exactly to your specifications, but you bear all the costs and maintenance responsibilities. Organizations choose private clouds when they have strict regulatory compliance requirements, need to maintain legacy systems that can't easily move to public clouds, or require guaranteed performance levels that shared infrastructure can't provide. For example, a government intelligence agency might operate a private cloud to maintain complete control over classified data and ensure it never resides on infrastructure shared with other entities. Community clouds serve a specific community of organizations that have shared concerns, such as regulatory requirements, security considerations, or mission objectives. The infrastructure is shared by several organizations, but remains isolated from the general public cloud. Imagine a community cloud like a private golf club. It's shared by members who meet specific criteria and have common interests, but it's not open to the general public. A perfect example would be a cloud environment specifically designed for healthcare organizations that need to comply with HIPAA regulations. Multiple hospitals and clinics share the infrastructure, which is specifically configured to meet healthcare compliance requirements, but it's isolated from organizations in other industries. This model provides some cost benefits of sharing resources while maintaining industry-specific security and compliance features. Hybrid clouds combine two or more distinct cloud deployment models, typically public and private, that remain unique entities but are bound together by standardized or proprietary technology that enables data and application portability. Think of a hybrid cloud like having both a personal vehicle and a public transit pass. You use each for different purposes based on your specific needs at any given time. Organizations use hybrid clouds to keep sensitive data in private clouds, while leveraging public clouds for less sensitive workloads, to handle burst capacity during peak demand periods, or to gradually migrate from on-premises infrastructure to public clouds. For instance, a retail company might keep customer payment data in a private cloud for security reasons while running their web application and product catalog in a public cloud for scalability and cost efficiency. Understanding these deployment models is crucial for making architectural decisions, and this knowledge is heavily tested on the exam. Each model has implications for security controls, compliance capabilities, cost structures, and operational responsibilities that you need to consider when designing cloud solutions. Let's discuss cloud computing roles and responsibilities, which define who does what in the cloud ecosystem. This is absolutely critical for the exam because many questions test your understanding of the boundaries between different roles. The primary roles include the cloud service provider, cloud customer, cloud broker, cloud carrier, and cloud auditor. Each role has specific responsibilities and relationships with the others. The cloud service provider, or CSP, is the entity that makes cloud services available to customers. They own or lease the data centers, purchase and maintain the hardware, develop or license the software platforms, and provide the network connectivity. Major CSPs like Amazon, Microsoft, and Google invest billions of dollars in infrastructure, employ thousands of engineers, and operate data centers around the world. The CSP's responsibilities vary depending on the service model. In IaaS, they provide basic infrastructure. In PaaS, they also manage operating systems and middleware. And in SaaS, they handle everything, including the applications. CSPs must ensure service availability, maintain security of the infrastructure, comply with relevant regulations, and provide clear service level agreements to their customers. The cloud customer is any individual or organization that uses cloud services. This could be a Fortune 500 company using AWS for their entire IT infrastructure, a small business using QuickBooks Online for accounting, or an individual using Google Drive for personal file storage. As a cloud customer, your responsibilities also vary by service model. In IaaS, you're responsible for everything from the operating system up, including all applications, data, and access controls. In SaaS, your primary responsibility is managing your data and user access. The key point for your exam is understanding that customers always retain responsibility for their data, regardless of the service model. You can outsource the processing and storage of data, but you cannot outsource the liability for that data. Cloud brokers are intermediaries that manage the use, performance, and delivery of cloud services and negotiate relationships between cloud providers and cloud customers. Think of them like travel agents for cloud services. They help customers navigate the complex landscape of cloud offerings, potentially combining services from multiple providers to meet specific needs. A cloud broker might help a company select appropriate cloud services, migrate applications, integrate multiple cloud services, or even provide value-added services on top of basic cloud offerings. Some brokers specialize in specific industries, helping ensure compliance with industry-specific regulations while optimizing cloud usage. Cloud carriers provide the connectivity and transport services that enable access to the cloud services. These are typically telecommunications companies and internet service providers that offer the network infrastructure, connecting customers to cloud providers. While often overlooked, carriers play a critical role in cloud service delivery. The quality, reliability, and security of network connections directly impact cloud service performance and availability. For mission-critical cloud applications, organizations often contract with multiple carriers to ensure redundancy and may implement dedicated network connections to cloud providers rather than relying on public internet connectivity. Cloud auditors are independent entities that conduct assessments of cloud services, operations, security, and privacy impact. They provide unbiased evaluations of how well cloud providers meet security standards, compliance requirements, and service level agreements. Auditors might assess a provider's security controls against frameworks like ISO 27001, SOC2, or FedRAMP, evaluate compliance with regulations like GDPR or HIPAA, or verify that service level agreements are being met. For your exam, understand that auditors provide critical third-party validation that helps customers make informed decisions about cloud providers and helps providers demonstrate their security and compliance capabilities. Speaking of making informed decisions, those practice questions I created cover numerous scenarios involving these different roles and their interactions. You'll encounter questions asking you to identify which role is responsible for specific activities or how responsibilities change across different service models. Working through these questions will help you internalize these concepts and recognize the patterns that appear on the actual exam. Now let's explore the building block technologies that make cloud computing possible. These foundational technologies are essential to understand because they enable the characteristics and capabilities we've been discussing. The primary building blocks include virtualization, storage technologies, networking, database systems, and orchestration platforms. Virtualization is arguably the most important building block of cloud computing. It allows multiple virtual machines to run on a single physical server, each isolated from the others, and running its own operating system and applications. This technology enables the resource pooling and rapid elasticity characteristics of cloud computing. There are several types of virtualization you need to understand. Server virtualization, which we just described, allows multiple virtual servers on single physical hardware. Storage virtualization abstracts physical storage from multiple devices into what appears to be a single storage pool. Network virtualization creates virtual networks that are independent of the underlying physical network hardware. Desktop virtualization delivers desktop environments as a managed service. Each type of virtualization contributes to the flexibility and efficiency of cloud computing. Let me explain how virtualization works with a concrete example. Imagine a physical server with 128 gigabytes of RAM, 32 CPU cores, and 10 terabytes of storage. Without virtualization, this server might run a single application that only uses 20% of its capacity, wasting the remaining resources. With virtualization, you could run 20 virtual machines on this same server, each allocated 6 gigabytes of RAM, 2 CPU cores, and 500 gigabytes of storage. Each virtual machine believes it's running on dedicated hardware, completely isolated from the others. One VM might run a web server, another a database, another a development environment, and so on. The hypervisor, which is the software layer that enables virtualization, manages resource allocation, ensures isolation between VMs, and handles the translation between virtual and physical resources. Storage technologies in cloud computing go far beyond traditional hard drives. Cloud providers use sophisticated storage systems that provide redundancy, performance, and scalability. Object storage systems like Amazon S3 store unstructured data as objects in buckets perfect for photos, videos, backups, and static website content. Block storage provides raw block-level storage that can be attached to virtual machines similar to traditional SAN storage. File storage provides shared file systems accessible by multiple systems simultaneously. Content delivery networks cache frequently accessed content at edge locations close to users, dramatically improving performance for global applications. Each storage type has specific use cases, performance characteristics, and pricing models that you need to understand for both real-world application and exam success. Networking in cloud computing involves complex software-defined networking that provides isolation, security, and flexibility. Virtual private clouds allow customers to create isolated networks within public cloud infrastructure. Software-defined wide area networks connect multiple sites and cloud resources. Load balancers distribute traffic across multiple servers to ensure availability and performance. Virtual private networks provide secure connections between on-premises infrastructure and cloud resources. Understanding these networking concepts is crucial because they determine how data flows between components, how security boundaries are established, and how applications achieve high availability and performance. Now let's discuss some critical security concepts relevant to cloud computing, as security is woven throughout every aspect of cloud architecture and operations. The shared responsibility model is perhaps the most important security concept you need to understand for your exam. This model clearly delineates security responsibilities between cloud providers and customers, and these responsibilities shift depending on the service model you're using. In the shared responsibility model, cloud providers are responsible for security of the cloud. This includes physical security of data centers, hardware security, hypervisor security, and the underlying infrastructure. Customers are responsible for security in the cloud. This includes data encryption, identity and access management, application security, and operating system hardening in IaaS environments. The key insight is that you can never outsource responsibility for your data security, only the implementation of security controls. This concept appears repeatedly on the exam in various forms, testing your understanding of who is responsible for what in different scenarios. Data security in cloud computing involves multiple layers of protection. Encryption is fundamental, and you should understand encryption at rest, encryption in transit, and encryption in use. At rest, encryption protects data stored on disks, in databases, or in object storage. In transit, encryption protects data as it moves across networks, typically using protocols like TLS or IPsec. Encryption in use, though still emerging, involves technologies like homomorphic encryption that allow computations on encrypted data without decrypting it first. Key management is equally critical. You need to understand who controls encryption keys, how they're rotated, and how they're protected. Many compliance regulations require that customers maintain control of their encryption keys, even when data is stored in public clouds. Identity and access management in cloud environments is complex because you're dealing with multiple types of identities: human users, service accounts, applications, and devices, across potentially multiple cloud providers and on-premises systems. Federation allows users to authenticate once and access resources across multiple systems. Multi-factor authentication adds additional verification beyond passwords. Role-based access control ensures users only have the permissions necessary for their job functions. The principle of least privilege should guide all access decisions. For your exam, understand different authentication protocols like SML, OAuth, and OpenID Connect, and how they enable secure access to cloud resources. If you're finding some of these security concepts challenging, don't worry, that's completely normal. Security in cloud computing is complex because it involves multiple layers, shared responsibilities, and constantly evolving threats. That's precisely why I included detailed security scenarios in those free practice questions. Working through real-world security situations will help solidify your understanding and prepare you for the types of security questions you'll encounter on the exam. network security in cloud computing requires a different approach than traditional on-premises security. In traditional environments, you might rely heavily on perimeter security, firewalls at the network edge protecting everything inside. In cloud computing, the perimeter essentially disappears. Resources might be distributed across multiple regions, accessed from anywhere on the internet, and dynamically created and destroyed. This requires a zero-trust security model where every connection is verified, every resource is protected individually, and security policies follow workloads regardless of location. Security groups and network access control lists provide granular control over network traffic. Web application firewalls protect against application layer attacks. DDoS protection services handle volumetric attacks that could overwhelm your applications. Compliance and governance in cloud computing present unique challenges because data might be processed and stored in multiple jurisdictions, each with its own regulatory requirements. You need to understand data residency requirements. Some regulations require data to remain within specific geographic boundaries. Data sovereignty issues arise when data is subject to the laws of the country where it's stored. Privacy regulations like GDPR in Europe, CCPA in California, and various national privacy laws impose strict requirements on how personal data is collected, processed, stored, and deleted. For your exam, focus on understanding how different deployment models and service models impact compliance capabilities, and how shared responsibility affects compliance obligations. Disaster recovery and business continuity in cloud computing offer both opportunities and challenges. Cloud computing can significantly enhance DR and BC capabilities through geographic distribution, automated backups, and rapid resource provisioning. You can replicate data across multiple regions, quickly spin up replacement infrastructure, and even implement active-active configurations where applications run simultaneously in multiple locations. However, you also need to consider new risks like provider outages, data repatriation if you need to leave a provider, and dependencies on network connectivity. Understanding concepts like recovery time objectives, recovery point objectives, and how different cloud architectures support different DR strategies is essential for your exam. Cost management in cloud computing requires continuous attention because the pay-as-you-go model that makes cloud attractive can also lead to unexpected costs if not properly managed. You need to understand different pricing models: on-demand, reserved instances, spot instances, and committed use discounts. Resource tagging helps track costs by project, department, or application. Auto-scaling should be configured with cost constraints to prevent runaway expenses. Cost optimization involves right-sizing resources, identifying and eliminating unused resources, and leveraging appropriate pricing models for your usage patterns. Many exam questions test your understanding of how different architectural decisions impact costs and how to optimize cloud spending while maintaining performance and availability. As we wrap up this comprehensive overview of cloud computing concepts, architecture, and design, remember that these fundamentals form the foundation for everything else you'll learn about cloud security. Every security control, compliance requirement, and architectural decision builds upon these core concepts. Take time to really understand not just what these concepts are, but why they matter and how they interrelate. I want to emphasize once more that success on your Managing Cloud Security D320 exam requires not just memorizing facts, but understanding how to apply these concepts in real-world scenarios. That's why those 300+ free practice questions I've developed are so valuable. They present you with situations similar to what you'll face on the exam and in your career, helping you develop the critical thinking skills necessary to succeed. You'll find questions that combine multiple concepts, require you to analyze trade-offs, and test your understanding of how different cloud characteristics, service models, and deployment models work together. Remember, cloud computing is constantly evolving, but these foundational concepts remain consistent. Whether you're designing a cloud migration strategy, implementing security controls, or preparing for your exam, always return to these fundamentals. Understand the 5 essential characteristics. Know the service models inside and out. Recognize when each deployment model is appropriate And never forget the shared responsibility model that underlies all cloud security. Your success on the Managing Cloud Security D320 exam depends on mastering these concepts, but more importantly, understanding them will make you a more effective cloud security professional. Take advantage of all the resources available to you, including those free practice questions. And remember that every concept we discuss today will appear in various forms throughout your exam. Stay focused, keep practicing, and you'll be well prepared to ace your OA exam and excel in your cloud security career. Good luck with your studies, and I'll see you in the next chapter where we'll dive deep into cloud data security.